Hi. So my name is Shubham Rateria. I am currently the co-founder and CTO at Custiv, and I'm here to talk to you guys about building real-time and collaborative applications. So these can be web applications, mobile applications, or any sort of applications in general. Before I start my talk, I actually want to talk to you guys about the inspiration behind why I wanted to talk about this, why we are building on something like this and the applications of it, etc., etc. So at Custiv, what we do is at Custiv, we build software for manufacturing. So we are a digital contract manufacturing platform where we work with clients like L&T, Adani's, Tatas of the world for handling the complete manufacturing projects. So in manufacturing, there are multiple stakeholders across the board who use a piece of software. So what happens is using one web platform, and if someone updates something on one side, the update has to be propagated throughout the system to the other stakeholders who are using that software. Similar examples are softwares like Figma, Google Docs, Google Sheets, Notion, Miro, etc. Right. So previously, like before founding Custiv, I worked extensively across banking and healthcare, building software applications for massively across those two sectors. And in those two sectors, I faced similar problems of being able to build collaborative applications fast. Because if, as anyone here worked on such platforms where you've had to build software where multiple people have to be on the same side and do that stuff, no, not at all. Like, right? So if you've built systems like that, you would generally tend to use things like Firebase or real-time databases, PouchDB, CouchDB, and have to set up your own channels for transmitting data, etc., etc. A lot of engineering goes into the system. Plus, managing networking is a big pain. Scaling backend systems again is a big pain, right? So it's not very straightforward to be able to build these systems. But today software is going towards the point where collaborative software is becoming a need of the hour, especially for developers like you and me who have to write such software without having to spend so much time on this piece. We should spend our time on better things to build. Right. So which is why I wanted to talk to you about. Now, this talk is going to be very conceptual. It's not going to go extensively technical. Technically, it's not a technical oriented talk. It's more to give you. It's more for you to get some appreciation on what it takes for someone. Say someone at Figma to be able to build the software that they are building, and how does that software scale and how does that software function. Right, so to start off with, we'll just define the terms. What is a real-time application? What is a collaborative application? These two are two separate things. So a real-time application essentially just means that data from one system has to be shown to other systems whenever there is a change on system one. So now examples of this are real-time dashboards, your financial systems where data has to be constantly updated, and the general architecture of such systems is that these are connected by sockets, and generally by sockets you can have other network protocols as well, but there's a source and there's a sink. There is someone who is creating the data, and there's other people who are ingesting, like who are consuming that data, right? So for example, in a real-time dashboard, there is someone who is going to be changing those parameters. So in a manufacturing setup, for example, there will be information from machines will be changing those parameters, and you and I who are using the software will be able to see those details on our screen updating in real time. Now, collaborative applications, on the other hand, need to transmit data in real time, and also the data needs to be in sync across the clients. Now, this second point brings in a lot of engineering overhead. Why? Because your nodes now have to be both a source and a sink. Like, you have to consume that data, but you also need to produce to be able to produce that data which syncs across different clients. And examples, obviously, as I said, was things like your Google G Suite, Figma, and Miro. What goes into building collaborative applications is now what we'll talk about. So throughout this talk, I'll just use a simple example of building something as simple as a to-do application, which simply is just an array of objects which contains a text and whether or not that to-do is done. Simple as that. Now, what we will be building is, say there are three nodes, Alice, Bob, and Charlie. These are the three clients or whoever is using the software. They are now and this software has to run on all of these three clients, and they should be able to see whoever is changing, and they should also be able to propagate their own updates. Right? So just basic requirements of a collaborative application. So if I'm building something like this, what does it need to be? So first of all, collaborative and multiplayer software are a problem of distributed systems. If any one of you here has worked on distributed databases, this problem is the most similar to that, because you need to have data replicas on each node, and those data replicas need to be in sync. There's one changer that I will talk about, but essentially the problem boils down to a data replication problem, which is a well-researched problem in distributed systems. Second, the data must be strongly consistent for every collaborator. Now, what consistency means is that everyone needs to be on the same state of data at any given point of time, right? Because if we diverge, for example, if you use something like Git, in Git, when you diverge, like when multiple developers are working and someone diverges and you need to merge your changes back, you can do so manually. Like, you can tell the system what to merge and what not to merge. But in a software like this, the software needs to take care of those merges. It has to be automatic, and it has to be automatic in a way that it converges. What that means is that the decisions should be same for each node, so that everyone is always on the same state. Because once you diverge, there are a ton of problems that happen to make you come back to the original state, and the replications are very, very bad, because that can change data on your backend. Some user will just be shown some random garbage and things like that. And absolutely terrible. So, and collaborators should also be able to write at the same time. Again, this is the collaborators can be a source and a sink problem, right? You have to be able to see the updates in real time and also be able to write to the system in real time. Local first. Now, this is a very interesting topic. What happens is, for example, say if you work on a system like Google Docs, Google Sheets, any of G Suite software, say two people are working on Google Docs together. One of you goes offline, both of you go offline for that matter. You have one copy of the document, you've made your changes. When you come back online, it absolutely, the resulting output is absolutely garbage, by the way. Like, I don't know if you've ever used it, but if it's the same document, editing the same paragraph, it's absolute garbage. Why not, if we can, the problem here is, can we build systems that don't require central servers like Google Docs does, so that if you and I are connected to the same hotspot, we have the application loaded on our front end. If I'm making the changes, why do I need to be connected to a server for my changes to propagate to you, right? So that's the whole concept of a local first application, that I should be able to work offline. When I go back online, my changes should merge with everyone in the network, and I should also get the changes that everyone else in the network has made, right? Partitions should not cause systemic failures. What a partition, I don't know if you guys, does anyone know here what the cap theorem is? Right? So what partitions generally mean is one node going offline, or one node just being disconnected from the system in simple languages. So that should not cause your entire system to fail. Like, if I'm writing a collaborative application, if there are 10 users using it, say even if 3 of them go offline or something bad happens to that application, something crashes, it should not affect the remaining system. What that also, from a developer's point of view, you have to think about what happens to your data then. Right? If 3 of the users have gone offline, crashed, whatever has happened, what happens to your data then? Right? So these are some basic requirements that a collaborative application needs to have. This is a very, very important term that we will talk about: strong eventual consistency. Now, this is a topic that is that separates the problem of distributed databases to the problem of collaborative applications. In distributed databases, all your replicas have to be in sync at any given point of time. There is no point where a replica A is not having the same data as replica B, right? So, extensively studied problem. Strong eventual consistency means that I don't have to be in sync with you at any given, like every given point of time. If I'm not in sync with you right now, I can be in sync with you in a time in the future, given the fact that I have received all the changes that you have made. So that is a assurance to the system that you as a developer have to give, right? As long as you can propagate the changes from one client to the other, the clients A, B, and C, X, Y, and Z will always be in sync in a given point of time. This is the assumption that we make. Right, now just quickly to talk about consensus and convergence. So consensus differs from convergence in a way that, say if I have 2 documents on Google Docs, right? Say if Alice types that the quick brown fox jumps over the lazy dog, and Bob also has the same text, then Alice makes a change changing the dog to cat. Bob makes a change changing the cat to the mouse. Consensus in the system would mean that I can have only one of each, like either of these two. Guys who who worked on blockchain will understand this concept well, right? So you can't have both the values. You'll have only one, right? So I can either have cat or mouse as my final state. Convergence, on the other hand, which is very, very important for collaborative applications, means that I have to have both. I can't ignore a user's changes, right? Because if I'm editing that text and you are editing that text, I can't just go and say that I'm going to disregard your text. These algorithms can vary a lot depending on your end use case, but generally you can't ignore what other users are doing. So now, what does it take to build a collaborative to-do application? So let's consider three agents. All the three agents have an array of three items, three to-dos. Say Alice makes a change, and by the way, we will only consider two operations here. So we only consider that you can insert after an index and you can delete element at a specific index to just keep things very simple, right? So now say Alice inserts one, inserts after index 1 to do 2.5. They make the change to their local copy, and after making a change to their local copy, they propagate the changes to all the pairs. Now this can happen either through a centralized system or through a P2P system, depending on your use case. But as long as the changes have gone to the other pairs, they will also make changes to their local copy, and everyone stays in sync, right? But there are a lot of problems when you think about this from a computer networking perspective. There are a ton of problems that will happen to this. If anyone's written computer networks, you know this. Like, if anything that can go wrong will go wrong. Like, you can't just take anything for granted when you're writing distributed systems. Messages might arrive out of order. So in our example now, what happens when say Alice makes a change, but the changes don't go in this on, and say Bob makes a change, but changes don't go in the same order to your third agent, which is Charlie. So say I've done insert 0, 1.5, I've made change to my local copy, and then I've propagated the changes to my peers. Now what happens is, say they've received the changes. Immediately after receiving my change, Bob decides to make another change. Right now, think of it in this way: Bob and Charlie are very close by. Like, say Bob and Charlie are both sitting in Bangalore, sitting in this room, but Alice is far off in America, and there is around 250 milliseconds of latency that it takes for a packet from anywhere, say in San Francisco, to reach Bangalore, right? So that's a finite amount of time. That's a good amount of time to consider in any application like this. So Bob will now make that change. So you see the state of Alice and Bob currently are in sync. As soon as Bob makes that change, they will change their local copy, and they will propagate the changes to their peers. So it sends it to Alice and Charlie. But what happens is that Charlie gets Bob's packet first and then my packet, right? So now when Charlie applies these operations to their local copy, the dotted one is the one that they currently have, and then after first operation, and this is after second operation, right? They go out of sync. And for a system like this, there is no way to know which user is in sync or is not in sync, right? If you want to design something like that, it comes with tremendous overheads. Second problem, messages might arrive twice. What do you do? So for example, in this sort of a system, you have to ensure that the packets reach your clients at least once, right? That guarantee has to be given by the system. So say Alice makes this change. They say insert after 0, 1, 1, or 1.5. Right now, the message is sent to Bob. Bob makes a change on the local copy. They've sent back an ACK to Alice saying that, okay, I've received the thing, I've made that change, but that ACK does not reach back to Alice. There can be tons of reasons for this: some sort of packet loss due to network failure, due to some cable being cut somewhere, etc., etc., etc. Then but Alice has to send that packet to Bob, so they retransmit the packet saying that, okay, you have to insert after 0, 1.5. Bob has now made that change twice to the local copy, but Bob has no way to know whether or not this was intended, but they just assume that, okay, if Alice has sent me this instruction, I'm going to execute that onto my local copy. So how do we achieve data consistency and data convergence is what we are going to talk about now. So there are two ways, the two topics of research that are going extensively in distributed systems that help us to do this. First of which is something called operational transform. Operational transform, by the way, is how your Google Docs work. So Google Docs is a heavy and actually a very successful use case of OTs being able to be developed and put into practice at a massive scale. Because operational transforms are a group of algorithms where operations on any given data structure transmitted between clients are transformed in a way that state across the clients is maintained when they are executed, right? What this means is very simple. So for example, now again coming back to Alice and Bob. So say you have an array of 4 elements, but the thing about operational transform is you have to have a server in between. Every message has to go through a server because the server has to know what is happening to the data, etc. Right? So the server will also have their local copy. Now say, so yeah, they maintain all the data and all comms have to pass through it. Now say Alice makes this change, right? So they say they do insert 0, 1.5. After they've made that change, the data is sent to the server, uh, right? And at the same time, by the way, Bob has also made a change saying that you have to delete element at 2, right? Both of those packets are sent to the server. The insert 0, 1.5 comes first, then the delete 2 comes. But the server is smart enough to know that before the index 2, the element has been added. So you don't have to delete the element at 2. You actually have to delete the element at 3, because if you see the logic, if you see the thing on top, so if you do insert after 0, 1.5, but if you delete 2, things will go wrong. Things will just go out of sync. You don't know what's going on in the system, and the system breaks. It diverges. It can never converge back. So that's why they've transformed the operation to state that to be able to maintain sync across clients, and those are the operations that are now transmitted to your different clients. So your clients are now in sync. Pros and cons are obviously they've been developed successfully for data structures like strings and therefore also arrays, and have massive scale applications like Google Docs. They're extremely difficult to implement and debug. These algorithms have been a topic of research for almost 2 decades now, more than that actually. Extremely difficult to implement at scale. People at Google who did it are absolutely brilliant, but other people have tried it. Even guys at Figma, for example, tried it for a while, but really didn't work out for them. Extremely difficult to implement and debug. And yeah, and you now have a single point of failure. If anything in your server goes wrong, it's just gone, right? So your server becomes a single point of failure. It also becomes a bottleneck for throughput. So if you want to scale your systems, it's heavily dependent on your server to be able to handle that sort of bottleneck and horizontal scaling issues. The second and the more interesting point of research and things that have been put into practice are something called conflict-free replicated data types. As opposed to operational transforms, CRDTs are a data structure. They are not just an algorithm. These are a kind of data structure that have the properties of convergence built into them. So these allow you to replicate, to update any replica independently, concurrently, without coordinating with other replicas. So this family of data structure essentially lets you send your changes to anyone else in the world, and if they are also using the same data structure, you should be able to do it concurrently and without having to worry about what happens, and without having to worry about things going out of sync. It automatically resolves any inconsistencies that occur. Which means that in our previous example, when we saw that delete 3 and the insert example, those sort of things don't have to be taken care of now by a central server. Things in a data structure, the logic in the data structure itself takes care of that. Although replicas may have a different state at any particular point of time, they're guaranteed to eventually converge. So strong eventual consistency is the point that we had discussed about. This is also, by the way, used at SoundCloud, Redis, Facebook, and Apple. Redis, a lot of Redis data structures is built on CRDT. So if you ever study about how Redis scales the replicas, how it manages data across different servers, a lot of that is based on CRDTs. Figma also, by the way, uses this. So how do CRDTs achieve this? Now CRDTs achieve this by having 3 mathematical properties. Please don't kick me for taking you back to math class, but they have to be idempotent. Now what that means is that any update from one pair can be applied multiple times and the result should be the same, right? So that takes care of things like, say, message arriving twice problem. So if I'm sending you that same packet again and again, sending you the same instruction again and again, your data structure should be able to know that's the same instruction, and therefore either, and actually they can even apply it if they want, but if they don't, but they can choose not to apply it, but they have to maintain this property. Second is being commutative. Now commutative again means that changing the order of the operands does not change the result. Simply put, if you have if there's a binary operation on a set, it's commutative only if x op y is equal to y op x, right? In our case, x and y are states, and your op is the merge operator. So given two states, if you merge them, it doesn't matter if you merge A first and then B, like if you do A of B or if you do B of A, the output should be the same. The third is associative, which means that changing the order of parentheses in the operation does not really matter which. So if you have a binary of, if you have an operation on a set S, and if you change the order of the parentheses, the output is still the same. What commutative and associative in our case mean is that we don't have to worry about ordering, because ordering in networking is a huge pain. So it doesn't matter how you're setting up your system, maintaining that sequence is absolutely huge pain, and things go wrong. And in our case, the penalty of something not being in order is absolutely terrible, because you can just completely diverge from your main state, and coming back now to your original state it's absolutely difficult. So you have to not worry about order, which is what the last two properties give you. You can use any sort of networking protocol. So I don't want, so in this talk, for example, I don't want to go into the details of being able to develop systems like this, right? Because there are a lot of implementations out there, and that actually deserves a whole series of lectures to itself. Like you'll have to go a lot, you'll have to understand things like order theory and stuff like that to be able to understand how these data structures actually work. But even understanding basics of this will help you use data structures out there. For example, there are solutions like YJS, AutoMerge, etc., that will help you build applications like this. Right, to be able to just use the data structures out of the box and to be able to build applications like this. Networking protocols. So we didn't talk about networking because networking is a well-studied topic, and a lot of you here, all of you here, in fact, who have developed applications that have used different networking protocols. So some common networking protocols that we can use here is WebSockets, your WebRTCs, mesh networks, and gossip protocols. The thing with CRDTs now is that since you don't need a central server for being able to coordinate and do things between multiple replicas, you can just do peer-to-peer. So in our first in our first discussion, say if I'm building Google Docs based on CRDTs, I now don't need to be able to be connected to a central server. So if all of us here are sitting in the same room, we have a copy of the app loaded, we are connected to the same Wi-Fi network, we can all just collaborate on that data. And once any one of us comes online, it's connected to the internet, all of that data is now synced with your backend, right? These are common implemented. So all of these data structures, for example, are well studied in the CRDT ecosystem and have been implemented well. So you can just use any of this out of the box and be able to use all of this in your applications. Again, it comes with its own pros and cons. Pros is, yes, you get strong eventual consistency. There's no dependency on a central server, so you can transmit P2P. There's low complexity because you don't have to develop intensive algorithms to be able to do all of this stuff. Because I gave you problems, I gave you just two problems in networking. So your server packets arriving twice, or your packets arriving out of order. But there are a lot of things that can also go wrong, and the permutation combination of that can lead your OT algorithms to just go crazy, which is also why they're absolutely difficult to be able to implement and to be able to execute. But with CRDT, since you don't have to worry about a central algorithm, it's all of that logic is built into your data structure. You can just use that out of the box and not worry about all of that complication. But the con here is a huge amount of metadata is stored on your data structure for you to be able to allow this. Now, just to give you an example, say if you're using an array, the typical size of a CRDT array would be anywhere from 3 to 5 times the original size of your array at minimum, because it needs to store a good amount of information for it to know what is going on and for it to be able to do all of these things that we have spoken about. Cool. So after, am I going too fast? That's fine. Okay. So after doing all of this, so I've been studying this problem for some time now. I've been very interested in this because there is no out-of-the-box solution for developers like you and me to be able to use and develop systems like this. It takes, if you study Figma's problem, Figma has been working on this for a very long time, and it took them a couple of years to be able to crack multiplayer extensively at the scale at which they are doing right now, right? So for startups like mine and for our teams, it becomes very difficult to be able to develop real-time collaborative systems, even develop basic features, and it takes an insane amount of engineering, which is why I wanted to work on a software package called Wire. I know there's a Web3 Wire also, but the software package called Wire, because the thought process was, what if we had a JavaScript object that was a CRDT and also a real-time shared data type? So if there is a JavaScript map that you're using, and if you change something on your system, the change reflects automatically onto every connected pair uh, of that data structure. Like, what if you can just build that into JavaScript itself? Is what the thought was when I started building this. So how? So now, for example, I have a beta out there. I'll talk about the demo also in a bit. But how does it work right now? So right now, how it works is there's a hook. So there's a use sync hook that we provide you. So if you use that hook, you give a unique data ID to your data, and you give it any JavaScript data structure in the data field over there. Then you just initialize the data. What happens is now this will register you to the backend. We do have a backend because we do some room management, but the longer goal is to be able to do P2P as well. So it registers you to the backend and syncs you with all your existing clients. But the return data structure, the data variable there now is a normal JavaScript object that if you use as a normal JavaScript object, syncs your data to everyone using the same ID. Now you have a JSON data structure that is a CRDT, so you can do collaboration on it, and the data structure itself handles real-time communication, so you don't have to worry about doing any of that stuff. You just have to use this hook and it does all of that magic out of the box. So that's what you get. So I'll just quickly walk you through some use cases and implementations of this. For example, so first quickly, so I'll just walk you through this. So here we write this hook. So the use sync hook that I showed you earlier, we'll just write this hook here and I'll just show you how that essentially works. So this hook, what the data structure, what our library does right now is basically you have a sync manager. So you create your data structure using that manager. You give it your data as a param. I'll not walk into what this does. So basically, ref ID is a unique ID that you have to give to the library for it to be able to initialize your data. And the last is you have to give it an onChange function. What happens when something changes? Now, this is a change function that will trigger either if you've changed it or any of your peers have changed this data. Right? You can use this system now to be able to build a hook that makes your app reactive and that serves as a local state variable for your app. So in this case, the use state exactly does that. So we have the line number 12 shows you this value that is basically incremented whenever there is a change that happens. Right? Does that make sense? Okay. Okay. So the next thing is how do we use this in an application? So similarly, how we were talking about problems in that to-do app, if you have something like this, you can just you just import that hook. You take that information, you give it your initial data, you initialize it with the room name. So room name here is basically a unique data ID, right? Anyone in the same room or having the same data ID will be able to be in sync, and you get this loaded data variable. This loaded data variable is now what becomes your sync data structure. Any change to this data in this manner, like for example, if you see here in our change handlers, whatever change we do to this data, we don't have to worry about any of the networking stuff. So you just make a change to that data structure and you can be assured that all of that will be propagated to your clients. I'll just start up a quick demo of this. Also, just 1 second. So now these are two separate windows, by the way. So two users are now in the same room. Right now, if user 1 adds any information, that information is propagated automatically to user 2, who doesn't have to really do anything now. So you use that information and you just update your state automatically. The state update is left to the developer, so you can decide how do you want to optimize your rendering. But you can just do that out of the box. So if anyone wants to enter anything, do any change, it's replicated in real time to the other users. It even supports text for now. right? So and all of this is happening real time, right? So it just happens automatically. Even merge conflicts that can otherwise happen over your wire, everything can is taken care of by the library. The second and more interesting example I want to get into is something that I'm sure some of you here have developed previously. Now, so this example essentially displays a present system, right? And we use it with generic data structures. I'll show you the code for this as well. But essentially what happens here is, using the same system now, you can build on top of it to be able to develop systems like awareness, systems like presence, things that happen on softwares like say Figma or Miro for all that matter. So in this example, you can see that the mouse position is being tracked. I am on the left side of the screen right now, so I'm moving my mouse on the left side of the screen. With some lag, you're seeing it on the right as well. Other things like mouse states, for example, right now I'm pressing my mouse button, so it updates the state on the other screen as well. If I'm dragging my mouse button, if I'm dragging my cursor, all of these things can be propagated across multiple clients, and you can build interesting software systems like this. So quick code for this is something like so, right? So here our data structure is so, like we only store the user's current mouse position, the state of the user's mouse right now, the name of the user, and the color of the user, because we assign a unique color to each user. And the rest of the code is really, really simple. We use it internally in the same way as you would to modify any data structure. So but the good thing about this is just that if you see the code, as a developer, you don't have to worry about anything. You just have to directly plug that value into your cursor. You just tell the cursor what the mouse position is. You just tell the cursor what the user name is. Just tell the cursor what the user color is, etc., etc., and the library takes care of the rest, right? Yeah, so that was my talk. Just wanted to come and talk to you guys about this, talk to you guys about something in how real-time collaborative systems are built. It was very brief. It was we just touched upon some basic topics, but if you guys have any questions, I'm sure my details will be on the React this events page, so you'll be able to find me. So if you have any questions right now, I'm up for taking them.